Okay, so let's go through exam 4. Problem 1, find the Taylor polynomial of degree 3 centered about a equals 4 for f of x equals root x. So first of all, I'd like to write down Taylor's formula. So Taylor's formula says that we can write a function f of x as the sum from 0 to infinity of an over n factorial x minus a to the n, where the an's are the nth derivative of the function evaluated at a. So in this example, our function f of x is root x, which we can write as x to the half. The first derivative of this function is 1/2 x to the negative half. The second derivative, when I bring the negative half down, I'll have a negative 1/4 x to the negative 3/2. Third derivative, when I bring the negative 3/2 down, I'll have a positive 3/8 x to the negative 5/2. That's as far as we're going to need to go because we're going to do a degree 3. So now we evaluate each one of these at a equals 4. So f of 4 is root 4, which is 2. F prime of 4 is 1/2 times 1 over root 4. Root 4 is 2, so this is 1/4. When we put 4 into the second derivative, we have our negative 1/4 out front. And we have 1 over 4 to the 3/2 power. The half power makes it a 2. 2 cubed is 8. 8 times 4 is 32. So we have a negative 1 over 32. And finally, when we plug in 4 to the third derivative, 3/8 out front, and a 1 over 4 to the 5/2 power. 4 to the 5/2 is 2 to the 5th, which is 32, times 8 is 256. So 3 over 256 is our fourth derivative at 4. So now when we go to write down this function, our first term, when n is 0, we don't have any x's and we don't need a factorial. So we're just going to have 2. Our second term, we have a 1/4 divided by 1 factorial. X minus 4 to the power of 1. Then we have a negative 1 over 32, 1 over 2 factorial, x minus 4 squared. And finally a positive 3 over 256 times a 1 over 3 factorial, x minus 4 cubed. So that's degree 3, so that's as far as we're going to go approximating here because we're only using degree 3. Okay, so let me just clean this up a little bit. 1/4 times 1 factorial is just 1, so this is 1/4 times x minus 4. Then we have minus 1 over 64 x minus 4 squared. And then we have plus 3 factorial is 3 times 2. So 3's will cancel and we'll have 256 times 2. So a positive 1 over 512 x minus 4 cubed. All right, so this is our Taylor polynomial of degree 3. In part B, what we would like to do is to use that polynomial to approximate the square root of 5. So remember what we did with approximations before. Square root of 5 for this function is exactly f of 5. Okay? And if we have a polynomial that approximates f of x, if I want to evaluate f of 5, I'm going to plug 5 into that polynomial. So we can say f of 5 is approximately 2 plus 1/4 5 minus 4 minus 1/64 5 minus 4 squared plus 1 over 512 5 minus 4 cubed. Okay, so we'll simplify that a little bit. This is just 2 plus 1/4 minus 1 over 64 plus 1 over 512. As a fraction, we get 1145 over 512. And this is approximately 2.23 638, 6328125. Find the radius and interval of convergence of the sum from k equals 1 to infinity, x minus 5 to the k over k times 2 to the k. So let's start with the ratio test. So L is the limit as n go, well, stay consistent here. Let's say k goes to infinity. Absolute ak plus 1 times 1 over ak. So we have the limit as k goes to infinity. X minus 5, k plus 1 over k plus 1 times 2 to the k plus 1 times the reciprocal of ak. Okay, so now let's do some simplifying. The x minus 5s are like base. We subtract the exponents. So we'll just get an x minus 5 to the 1 power. Likewise with the 2s, when I cancel, I'll just be left with the 2 in the denominator. And then we have a k over k plus 1. All right, now the absolute values, the only thing that could possibly be negative is the x minus 5. So everything else can get pulled out of the absolute value. And the limit, only the k's have a limit on there. So we can write this as the absolute value of x minus 5 over 2 is relative to the limit. That's all constant. And then the limit as k goes to infinity of k over k plus 1. Okay, and just a side note, the limit as k goes to infinity of k over k plus 1. We could say, oh, if I plug in, that's infinity over infinity. So using L'Hopital's rule, you could say this is 1 over 1 plus 0, which is 1. So then this limit is equal to x minus 5 in absolute value over 2 times 1. The ratio test tells us that we have convergence when L is less than 1. So we'll have convergence when the absolute value of x minus 5 over 2 is less than 1, or the absolute value of x minus 5 is less than 2, negative 2 is less than x minus 5 is less than positive 2. If I add 5 to everything, we'll have 3 less than x less than 7. What we don't know is what happens at the two endpoints. So let's check those. So let's check x equals 3. So I'm going to rewrite this series where I plugged in x equals 3. So we'll have the sum from 1 to infinity of 3 minus 5 is negative 2 to the k over k times 2 to the k, which is the sum from 1 to infinity, negative 1 to the k times 2 to the k over k times 2 to the k, and these 2 to the k factors cancel. So we have an alternating series. Okay, so we need to check two conditions. The first condition is that the AKs are decreasing, or sorry, we typically write some BKs, right? If I write BK plus 1, that's 1 over k plus 1. That's smaller than 1 over k, which is BK. So the next term is smaller than the previous term, so that shows that it's decreasing. The next thing we need to check is that the limit as k goes to infinity, BK is 0. If I take a limit as k goes to infinity of 1 over k, that is indeed 0. Okay. So this converges by the alternating series test. Next, let's check x equals 7. So we will have the sum from k equals 1 to infinity, positive 2, 7 minus 5 is 2, to the k over k times 2 to the k. 2 to the k over 2 to the k cancel. And the two ways that we could easily show that this series does not converge is either by recognizing that this is the harmonic series, or by or by labeling it as a p-series with p equals 1. Since the series converges at x equals 3 and diverges when x is 7, the interval of convergence is 3 to 7. Set up. Including the 3, but not the 7. Problem 3. Use a power series to find the integral of e to the x cubed dx. What we're going to do is start with a power series for e to the x. E to the x is the sum from 0 to infinity of x to the n over n factorial. Okay, so e to the x cubed, replace x with x cubed on the left, I replace x with x cubed on the right. So I will have the sum from 0 to infinity of x to the 3n over n factorial. So now I have a series for my function, and that's what I want to integrate. So the integral of e to the x cubed dx is the integral of this series, and for a series that converges, which power series do, I can break this up term by term, and I can integrate the terms of the series individually. I want to integrate this. I'm just going to use the power rule. So we add 1 to the power, and we divide by the new power. Okay, and there's some arbitrary constant that could be hanging around, like usual when we integrate. So that is a series for our representation for our integral. Okay, now let's find a power series for this function, x over 9 plus x squared. What I'm going to do with this one is I'm going to start off by saying I know that 1 over 1 minus x is the sum from 0 to infinity of x to the n. I'm going to say, well, I'd like a 9 in there, so let's multiply both sides by 1/9. Okay, and now what I would like to do is I would like to replace negative 9x with a positive x squared. But I can't replace the negative 9. I can just do a substitution for x. So I want to cancel the negative and cancel the 9 and turn the x into an x squared. So what we're going to do is we're going to take an x and we're going to replace it with a negative to cancel the negative, 1/9 to cancel the 9, and an x squared so that we have an x squared there. Okay, so what we're really doing is composition, right? We're composing both sides with negative 1/9 x squared. So if I replace this x and compose it with a 1/9 x squared, I'll have the same thing as last time. 1 over. Sorry, the negative 9 and the negative 1/9 will cancel, and so we'll just get plus x squared. So we do the same thing on the right. I'm replacing the x with a negative 1/9 x squared. So I have a negative 1 to the n. X squared to the n will give me an x to the 2n. And we'll have a 9 to the n. Okay. And now to get my function f of x, I'm going to multiply both sides by x. So let's clean this up a little bit. 1/9, and I have a 9 to the n in the denominator, so this is going to be a 9 to the n plus 1 denominator. We have a negative 1 to the n. X to the 2n times x will be an x to the 2n plus 1. So that is a power series for our function. Okay, find a Maclaurin series for g of x equals 1 over 1 plus x squared, and then use that to find a Maclaurin series for arctangent of x. So let's start off by saying 1 over 1 minus x is the sum from 0 to infinity of x to the n. And I want to replace the x with a negative x squared. So on the left, I have 1 over 1 minus negative x squared. On the right, I have the sum from 0 to infinity, negative x squared to the n. Let's simplify both sides. On the left, the negatives cancel, and we get 1 over 1 plus x squared, which was our goal. And on the right, we get the sum from 0 to infinity. I'll have a negative 1 to the n, x squared to the n. When we raise it, an exponent to a power, we multiply the powers, so it's an x to the 2n. All right. Now, we're going to use that to find a series for arctangent x. And I know that if I integrate this 1 over 1 plus x squared, I'll get arctangent of x. Okay, so on the left, when I integrate, we'll have arctangent of x. On the right, when I integrate, I'm going to get sum from 0 to infinity, negative 1 to the n. When I integrate x to the 2n, I'll get x to the 2n plus 1 over 2n plus 1. Okay, and we know when we integrate, we get a plus c. So if I integrate both sides, I get this plus c. What we want to do is make sure that the two sides line up. So if I plug in 0 on the left, I'll just have c. Maybe I should use a c and a c hat just to be clear. So if I plug in x equals 0, we'll get c. And if I plug in x equals 0 here, I'll get 0. So the constants are the same. So what I can do is I can just say, well, if I just want arctangent, then I'll just leave the constants off. So arctangent x is the sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Find a Maclaurin series for x minus arctangent x over x cubed. We have to be a little bit careful with this one. If I write out the first few terms of my arctangent series, when n is 0, I'm going to get a positive x to the over 1. Okay. Then when n is 1, I'm going to get a negative x cubed over 3. And then when n is 2, I'm going to get a positive x to the 5th over 5. And then x to the 7th over 7, right, and so on. Okay, so if I take x minus arctangent of x, it's going to do two things. It's going to get rid of my very first term, and it's going to switch all of my negatives. X minus, well, let's do this one step at a time. Well, let's just go ahead and write it. So the subtraction will cancel my first term. So when I write my series, I just want to get rid of the first term. So we'll start at counting at 1 instead of at 0. And it's going to throw a negative on everything. So I want to swap my negatives, right? Instead of being on n, I want it to be n plus 1. So that when I plug in a 1, instead of getting a negative, I'll get a positive. Right? So just so that you can see what happened there, when n is 1, I'll get a positive x to the 3rd over 3. When n is 2, it'll be a negative squared, so I'll get, I'm sorry, when n is 2, it'll be 2 plus 1 is 3. I'll get an odd power, so I have a minus. 2 times 2 plus 1 is 4 plus 1 or 5, so x to the 5th over 5. And it'll alternate from there. Okay, so you can see that we got rid of the first term, and we changed the sign on all the terms. Okay, now we'll divide by x cubed. When I divide by x cubed, well, let's just go ahead and write it. So I have x to the 2n plus 1 over x cubed. When I divide, I can subtract the exponent, so 2n plus 1 minus 3 will be a 2n minus 2. Okay, and that's our series for function f of x equals x minus arctangent x over x cubed. Okay, finally what we want to do is approximate x minus arctangent x over x cubed, approximate the integral of this from 0 to 1 using a Maclaurin polynomial with 3 non-zero terms. Okay, so if I now write out what these terms look like, when n is 1, I'll have an even power, so it'll be positive. I'll have 2 minus 2, which is 0, so x to the 0, so I don't have an x here, over, when n is 1, I'll have a 3, so I just get a 1/3, okay, which lines up. I should get what I had previously, just divided by x cubed. Okay, when n is 2, 2 plus 1 is 3, so I have a negative. When n is 2, 2 times 2 is 4 minus 2 is 2, so I have an x squared. When n is 2, I'll have 4 plus 1 is 5. When n is 3, 3 plus 1 is 4. That's a positive, or sorry, that's an even power, so I'll get a positive term. When n is 3, we'll have 6 minus 2 is 4, x to the 4th then. When n is 3, I'll have 6 plus 1, which is 7. Okay, so that's the first 3 terms of my series. So what we're going to do is we're going to say, all right, x minus arctangent x over x cubed is approximately 1/3 minus x squared over 5 plus x to the 4th over 7. So the integral from 0 to 1 of x minus arctangent x over x cubed dx is approximately the integral from 0 to 1 of 1/3 minus 1/5 x squared plus 1/7 x to the 4th dx. And now I integrate away. So I get 1/3 x, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power. So I have 1/3 x minus 1/15 x cubed plus 1/35 x to the 5th, which is 1/3 minus 1/15 plus 1 over 35 when I plug in 1, and 0 minus 0 plus 0 when I plug in 0. So I have a 1/3 minus a 15th plus 35th, which gives me 31 over 105 if I want a nice exact fraction, or as a decimal, 0.2952380952. And that's the test.